So in this video, what I want to do is use the Maclaurin expansion for 1 over 1 minus x, this geometric series, and use it to find the Maclaurin expansions of log of 1 plus x and the arctangent of x. So what I'd suggest is have a go at doing each of those. This is the one to try first, I would say, and then detailed answers will be provided on the next slide. But have a go with pen and paper first. See you in a minute. Okay, welcome back. Let's look at this question here. So you can, of course, find the Maclaurin expansion of log of the modulus of 1 plus x directly from the formula, which I've written out here again. But we can also extract it immediately from this formula, which I think everybody should know off by heart. And by symmetry, we can use this to immediately write down the expansion for 1 over 1 plus x by rewriting that as 1 over 1 minus x. So everywhere here where we have an x, we can just replace it with a minus x, so there'll be a 1 minus x plus minus x squared, etc. So we can just immediately write this down. For the odd powers, it becomes minus x cubed. The even powers stay positive, x squared plus x to the fourth plus x to the sixth, etc. So now, we know if we differentiate the logarithm of mod of 1 plus x, we're going to get 1 over 1 plus x. Or to put it differently, if we integrate this, we will obtain the logarithm of the modulus of 1 plus x. So what we're saying is that the logarithm of the modulus of 1 plus x is the integral of 1 over 1 plus x with respect to x. So it's therefore the integral of 1 minus x plus x squared minus x cubed plus x to the fourth, etc. with respect to x. Now this is an indefinite integral, so we should add an integration constant, and we will see in a moment how to understand what that has got to be. But this set of integrals is very, very easy, and what it tells us is that the logarithm of the modulus of 1 plus x is x from the integral of 1 minus x squared over 2 from the integral of x plus x cubed over 3 from the integral of x squared, etc. And there is, of course, an integration constant. To fix the value of the integration constant, what we do is we insert a value of x into both sides and see what we get. And the sensible value of x to insert is x is equal to 0, because then all of these terms vanish. So from setting x is 0, we have the logarithm of 1 plus 0, so that's just the log of 1, which is equal to 0, is going to be equal to c. So the left-hand side is the log of 1 when x is 0, in other words it vanishes, and in the right-hand side all of these terms vanish and we're left with c. So our integration constant vanishes. And this tells us that the Maclaurin expansion of the log of the modulus of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4 plus x to the fifth over 5, etc. And I'm not going here to think about questions of convergence or anything like that. But this is indeed the expansion, and it's a good exercise to show that you regain this from this formula with f of x being the logarithm of the modulus of 1 plus x. Okay, let's now look at the second question. So the second question is a bit different because On the previous slide, we can calculate the Maclaurin expansion of the logarithm of the modulus of 1 plus x directly, but calculating the expansion of the arctangent of x is not very nice at all, and you're welcome to try to do it, and you'll start to see that although the first term or two are easy, it starts to get complicated, and you're not going to see necessarily the structure. So instead, what we recall is that the arctangent of x is the integral of 1 over 1 plus x squared with respect to x plus an integration constant. In other words, if you differentiate arctangent of x, you get 1 over 1 plus x squared, the integrand here. So this is the formula that we know of by heart, and all we do is everywhere we have an everywhere we have an x, we replace it by minus x squared. So we have 1 over 1 plus x squared is 1 over 1 minus x squared. And now we can just take this formula, and everywhere there is an x, we replace it by minus x squared. So 1 is 1, plus x is minus x squared becomes x to the 4th, and then it's minus x to the 6th, plus x to the 8th, minus x to the 10th, etc. So the arctangent is going to be given by the integral of this expansion here. And again, these are very easy integrals. There will again be an integration constant. It's actually going to vanish again. And we can perform these integrals. So we integrate 1 and we obtain x. And then it's minus x cubed over 3 plus x to the 5th over 5 minus, again, just adding 1 to the power x to the 7th divided by that new power 7, etc., plus an integration constant. And we see here the first term here is x, and this would be the constant term, but we recall that the arctangent of 0 vanishes, and that's just saying that the angle that is defined to be the arctangent of 0 is 0, the tangent of 0 is 0. So that tells us that the integration constant c is equal to 0. So we just have to write down this result. Arctangent of x is all of that without the integration constant. And that is our answer for the expansion. And that's the nice way of calculating it. So on the next slide, we're going to look at a slightly different example where instead of integrating, we're going to differentiate a Maclaurin expansion. And I'm going to set this as an exercise for you. So you may know the Maclaurin expansion of the sine function. If not, it is straightforward to calculate the first few terms from the formula for a Maclaurin expansion. And then since you know that the derivative of sine x is the cosine of x, what I would like you to do is from the expansion for sine x, simply write down the Maclaurin expansion for the cosine of x. So have a go at doing that with pencil and paper and come back after you've had a look at it. Okay, welcome back. Let me write out for you the solution on the next slide. So from the definition or from your memory, I hope you have obtained this. So the sine of x starts with x, there's no constant, sine of 0 vanishes, and then it has the value x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. You can write this series as a sum, starting at j is 0, and we have alternating signs, x to a power of 2j plus 1, so when j is 0, it's x to the 1, and then you just add 2 to it in every next term, so it's x to the 1, x cubed, x to the 5th, etc., and we divide by the factorial that goes with that. So this factorial is the same number in here as we have in the power, and these alternating signs means we start with a positive value, and then it's negative, positive, negative, etc. Now, the derivative of sine is cosine. That means you can immediately write out that the expansion for the cosine of x is going to be 1, because the derivative of x is 1, and then here you're going to bring a 3 in front, which will cancel with that, and you're going to reduce the power, so you're going to get x squared over 2 factorial. So it's 1 minus x squared over 2 factorial. And the same thing keeps happening here. The 5 partly cancels with the 5 factorial. So you reduce the power by 1 and you reduce the number in the factorial by 1. So it's x to the 4th over 4 factorial, and that's written here. And that is the structure of the Maclaurin expansion of the cosine, and you can rewrite that as a sum in that way. And with that, I'll stop this video.